Welcome to this video. In this video for A-level math students, we're going to take a look at how to solve quadratic equations in one unknown. So I may need to touch briefly on quadratic functions, but the main focus will be solving quadratic equations. But I'll just quickly explain what I mean when I use the terms quadratic expression, function or equation, because I am referring to different things when I use these terms. In what follows, a, b and c are assumed to be fixed constants, with a not equal to 0 and x is either a variable or an unknown. So a quadratic expression is one which can be written in the form ax squared plus bx plus c. Different values can be substituted for x to give different values of the expression. A quadratic function is a function which can be written in the forms y equals ax squared plus bx plus c, or possibly f of x equals ax squared plus bx plus c, where again x can be replaced with different values and so it's a variable, and each value of x gives rise to a corresponding value of y, or f of x for example. A quadratic equation is an equation which can be written in the form ax squared plus bx plus c equals 0, where x is an unknown and corresponds to certain fixed values called solutions. Of course, there may be no solutions to a quadratic equation, or there may be a repeated solution, or there may be two distinct solutions. There can never be more than two solutions to a quadratic equation though. And note that in these, a must be non-zero, otherwise ax squared plus bx plus c just reduces to bx plus c, which is not quadratic but is linear. The discriminant of a quadratic equation, written in the form ax squared plus bx plus c equals 0, is the expression b squared minus 4ac. And we have that if b squared minus 4ac is greater than 0, then the equation ax squared plus bx plus c equals 0 has two distinct real solutions. If b squared minus 4ac equals 0, then ax squared plus bx plus c equals 0 has a repeated solution. And finally, if b squared minus 4ac is less than 0, then ax squared plus bx plus c equals 0 has no real solutions. And for the case where b squared minus 4ac is equal to 0, I personally have a tendency to say that the equation has a repeated solution rather than saying a single solution. A repeated solution carries more information than a single solution. If you're unsure whether a quadratic equation has real solutions, then check the discriminant. Of course, there'd be no point in trying to solve a quadratic equation that doesn't have any real solutions, at least at this stage where we don't consider other types of solutions. However, I won't be making much use of the discriminant in this particular video, but I will be using it in other videos though. There are two main ways of solving quadratic equations. There's factorisation and there's using the quadratic formula. To solve a quadratic equation ax squared plus bx plus c equals 0 by factorisation, we look for an expression px plus q times rx plus t, so that ax squared plus bx plus c is identically equal to px plus q times rx plus t, and in that case the solutions will be x equals minus q over p, or x equals minus t over r. I'll give some examples shortly of how to solve quadratics by factorisation. And now we look at the quadratic formula. So for a quadratic equation ax squared plus bx plus c equals 0, the solutions are given by x equals minus b plus the square root of b squared minus 4ac over 2a, and x equals minus b minus the square root of b squared minus 4ac over 2a, which are usually combined into a single expression called the quadratic formula, and this is x equals minus b plus minus the square root of b squared minus 4ac over 2a. I'll show in the extra stuff section to this video how to prove the quadratic formula. Personally, I would always have a preference for factorisation to solve a quadratic equation. Of course, the quadratic formula comes in useful from time to time, especially when a factorisation is not easily obtained, for example. It's very usual in pure mathematics to express your solutions in an exact form. For the solutions to quadratic equations, this will often mean leaving your solutions in surd form, for example. For mechanics and statistics, it might not be appropriate to leave your solutions in surd form, and in some cases, even in pure mathematics, it may be appropriate to use decimal approximations. However, my rule of thumb is that for pure maths, unless you are specifically told to express your answer in a decimal form, or unless there really is no reasonable way to express a number in an exact form, then always express numbers in an exact form by default. So let's have a look at some simple examples. You can find plenty of examples of how to factorize quadratics and basic applications of the quadratic formula in whichever textbook you use or whichever online resources, videos, things like that you might happen to use as well. So I won't repeat what's already available, but let's have a look at some problems which involve quadratics. Solve n plus 1 times n plus 4 equals 270. So I'm going to give two ways of solving this equation, a long way and a short way. So let's start with the long way. So we start by expanding out the brackets to give n squared plus 5n plus 4 equals 270, and rearranging this gives n squared plus 5n minus 266 equals 0. And this is, of course, of the form ax squared plus bx plus c equals 0, and so we can solve this quadratic equation by either factorisation or by using the quadratic formula. So I'm going to go for factorisation. So, of course, I'm looking for an expression of the form n plus p times n plus q, which, when expanded out, will give n squared plus 5n minus 266. So the product of the two numbers p and q must be minus 266. Therefore, one number must be positive and the other negative. Moreover, the sum of the two numbers should be plus 5, meaning that the positive number should have an absolute value exceeding that of the negative number by 5. So of course it may take a bit of hunting around, although I know that 15 times 20 multiply together to give 300, which is a bit too big. So how about 14 and 19? Well, 14 times 20 is 280, so subtract a 14 off that gives 266. So the two numbers are minus 14 and 19. So my factorisation is n minus 14 times n plus 19 equals 0. So of two numbers whose product is 0, at least one of the numbers must be 0. So either n minus 14 equals 0, in which case n equals 14, or n plus 19 equals 0, in which case n equals minus 19. And that's it. Now there is a potentially quicker way of solving this particular equation. My advice for solving this equation, or any other for that matter, is read the equation and understand what it says. And what I mean by this, in this particular case, is that the equation is clearly telling me to find two numbers whose difference is 3, because the difference of n plus 4 and n plus 1 is 3, and whose product is 270. Again, we may have to hunt around a little bit for the numbers, but since I know, for example, that 15 times 15 is 225, then let's try 15 times 18 as a possibility. 15 times 18 is 270, which is spot on. So n plus 1 equals 15, and n plus 4 equals 18, and so n equals 14. But of course that's only one solution. We also had a solution of minus 19 when we solved by factorisation. Well, don't forget that it may be two negative numbers that we multiply together to give positive 270. But which two numbers? Well, by symmetry of the problem, they must be minus 15 and minus 18. And so n plus 1 equals minus 18, and n plus 4 equals minus 15. N plus 1 must, of course, correspond to the smaller valued of the two numbers, and so we have that n equals minus 19. So the solutions are n equals 14 or n equals minus 19. So I'm not saying that either of these solutions is necessarily better in any objective sense than the other, but I personally prefer the second approach, but you have to choose which you prefer for yourselves. Solve the equation 3e to the power of x minus 4 equals 6e to the power of minus x. So I know from the outset that equations involving both e to the power of x and e to the power of minus x are probably going to be quite difficult to solve, but not always necessarily impossible to solve, at least without some algebraic manipulation. So I'm going to take a guess and multiply through by e to the power of x to give 3e to the power of 2x minus 4e to the x equals 6, which can be rewritten as 3e to the power of 2x minus 4e to the x minus 6 equals 0. And now, since this is an obvious hidden quadratic, then just to emphasize the quadratic-like nature of the equation, we can write 3e to the power of x all squared minus 4e to the x minus 6 equals 0. And if it helps, then you can make a substitution at this stage, something like z equals e to the power of x, to give 3z squared minus 4z minus 6 equals 0. I'll solve both with and without the substitution. So I can see that this equation doesn't easily factorise, so I'm going to apply the quadratic formula with a equals 3, b equals minus 4, and c equals minus 6 to give e to the power of x equals 4 plus minus the square root of minus 4 squared minus 4 times 3 times minus 6 all over 6. Or with the substitution, instead of e to the x, we have z. Simplifying this gives e to the power of x, or z, equals 2 plus minus the square root of 22 over 3. If you did make a substitution, then this would be a good time to resubstitute e to the power of x back in to replace the z. And of course we have that e to the power of x is greater than 0 for all values of x. And we have that 2 minus the square root of 22 is less than 0, since we know that the square root of 22 is greater than the square root of 16, which is equal to 4, which itself is greater than 2. And so 2 minus the square root of 22 over 3 is not a valid solution to this equation, which leaves e to the power of x equals 2 plus the square root of 22 over 3. And now, taking natural logarithms of each side gives x is equal to the natural logarithm of 2 plus the square root of 22 over 3. And yes, do leave your solution in an exact form unless you're told to do otherwise. So here we'll look now at some more complicated examples. As I've mentioned in some of my other videos, when it comes to this section, I'll try to explain my solutions more thoroughly, but there's never any suggestion that my solutions are anything more than just the solution that I happen to see at the time of making this video. If there are better solutions, then I leave you to discover these for yourself. I'm sure that there will be several much better ways of solving these problems, so I invite you to have some fun finding them. Solve the equation 4x squared minus 9x plus 22 over x plus 1 squared equals 2. So at first glance, this may not look like a quadratic, but we can't always expect our quadratics to come in some nice form. Sometimes we have to do a bit of work to put the equation into a more convenient and workable form. Of course, you have to be prepared to go ahead with an idea, even at the risk of that idea not working out in the end. My idea is to multiply through by x plus 1 squared to get rid of that inconvenient denominator on the left-hand side. So let's do that, and we get 4x squared minus 9x plus 22 equals twice x plus 1 squared. And now, really just follow your nose. So I'm going to try expanding out those brackets on the right-hand side. There's no guarantee that this is what I need to do, but it only takes a couple of seconds to do anyway. So I get 4x squared minus 9x plus 22 equals 2x squared plus 4x plus 2. And further simplification gives 2x squared minus 13x plus 20 equals 0. I can attempt to solve this using either factorisation or the quadratic formula. I'm personally always inclined to give factorisation a go first, so let's try that. If this expression does factorise, then it will have to look something like 2x plus p times x plus q equals 0. And the possibilities for numbers which multiply together to give 20, ignoring signs for the time being, are 1 and 20, 2 and 10, or 4 and 5. So I can quickly sift through the possibilities to see that 1 and 20 won't work, and 2 and 10 won't work either. However, I can see that twice 4 plus 5 is equal to 13, which gives me a bit of a clue as to what to do. And this leads me to the factorisation 2x minus 5 times x minus 4 equals 0. So I realise that the process by which I arrived at my factorisation may not seem to be very clear and systematic. All I can say is that if you understand what you're trying to do and what you're looking for when you want to factorise a quadratic, then with a bit of practice you'll develop your intuition and learn to quickly sift through possibilities. You'll find your own way of determining the factorisation of a quadratic, and that's a much quicker and more reliable way of factorising quadratics than any set method can ever be, because it's your own method and it means something to you. Anyway, since here we have the product of two numbers is equal to 0, then at least one of the factors must be equal to 0. We don't know which one, however, so we have if 2x minus 5 equals 0, then x equals 5 halves, and if x minus 4 equals 0, then x is equal to 4. and we're done. If you didn't see initially that the original equation could be expressed in the form of a quadratic equation, then it's not necessarily something to worry about too much. It may just be a sign that you need exposure to more quadratics in different contexts, but with sufficient practice, then you'll be doing rough rearrangements in your heads, I'd say almost automatically. And then even without having to put pen to paper, you'll be able to fairly accurately predict many of the different forms that a given equation can be rewritten into, and then be able to select the most appropriate for what it is that you want to do. It all comes with practice. So the next problem is, the sum of the first n natural numbers is Sn. Solve the equation Sn plus 18 minus 5Sn equals 3. So it's a formula that you do learn as part of your A-level maths studies, that Sn is equal to n times n plus 1 over 2. And so we have n plus 18 times n plus 19 over 2 minus 5 times n plus 1 over 2 is equal to 3. And so multiplying through by 2 gives n plus 18 times n plus 19 minus 5n times n plus 1 equals 6. And there's not really much to do here but to expand out and simplify to give n squared plus 37n plus 342 minus 5n squared plus 5n equals 6. And gradually simplifying, we get to n squared minus 8n minus 84 equals 0. This easily factorizes to give n minus 12 times n plus 8 equals 0. And so we have that n equals 12 or n equals minus 8. Of course, n is a natural number, so must be positive, and therefore the solution is n equals 12. So you need to be able to recognize quadratic equations when they come up in their various guises. And moreover, you need to be able to take the initiative yourself to solve quadratic equations when you see they need to be solved. Don't wait to be told to solve an equation. You need to just go ahead and do it. Of course, you'll need to select the method that you want to use to solve. Sometimes it may not be necessary to use factorisation or the quadratic formula, as we've seen in one of the examples that I've just given. When it comes to factorisation, there are all sorts of different techniques that supposedly make the process easier. In my opinion, these techniques are often very ineffective and distract you really from the best way of factorising quadratics, which is knowing and understanding what you're doing. If you understand what you're trying to achieve through a factorisation, then all of these miscellaneous techniques become effectively redundant. You will gain confidence in understanding factorising quadratics through practicing. No practice, no progress. It's that simple. Interpreting the solutions of quadratic equations is something that I'll leave for a separate video on quadratic functions. If you do want an extra challenge when it comes to solving quadratic equations, then the book Challenging Problems in Algebra by Posamentier and Salkind contains a section 14, called Quadratic Equations Fair and Square, which may be just the thing that you're looking for. And so here we are at the extra stuff section. Here we take a bit more detailed look at the concepts and ideas that I introduced in the previous parts of the video. Sometimes I prove things, sometimes I'll touch on historical or even philosophical aspects relating to these concepts. Whatever I feel like talking about, really. The aim is simply to give some more insight and depth to your understanding of mathematics. This section is largely optional. That is, most of what I cover in this part of the video, if not all of it, will not appear on an A-level maths exam. You don't need to learn it, you don't even need to watch it, unless you're interested to know a bit more about mathematics. But let's have a look at the proof of the quadratic formula to start with. Once you're in possession of the quadratic formula, then you have at your fingertips the solution to every quadratic equation. But that's not to say that other techniques for solving quadratic equations should be ignored or neglected. As with many general solutions, they're nice from a theoretical perspective, but they can be overkill in practice for some specific cases. General solutions consider the absolute worst case scenario. However, there will be many times when you come across quadratic equations that have some particular feature that you can take advantage of and which allows you to solve that particular equation much more quickly than using the quadratic formula. Learn to spot these things and you can keep your momentum going much better when solving problems. So suppose we have the quadratic equation ax squared plus bx plus c equals 0, where a, b, c are constants with a not equal to 0. Then since a is non-zero, we can divide through by a to give x squared plus b over a x plus c over a equals 0. And then completing the square, which I'll cover in another video, gives the expression shown on the screen now. And so with a bit more rearrangement, we end up with x minus b over 2a squared is equal to b squared minus 4ac over 4a squared. Taking square roots of each side and paying attention to the fact that we have a positive square root and a negative square root to account for, we obtain that x minus b over 2a is equal to plus minus the square root of b squared minus 4ac over 2a. And so x is equal to minus b over 2a plus minus the square root of b squared minus 4ac over 2a. And finally, x equals minus b plus minus the square root of b squared minus 4ac over 2a, which is of course the familiar quadratic formula. And from this, it's clear where the discriminant comes from and why, if the discriminant is negative, then the quadratic equation doesn't have real roots, since the square root of a negative number is not a real number. So now let's have a look at some of the history of quadratic equations. Quadratic equations, or at least something that is comparable to the modern notion of quadratic equations, were solved as far back as Babylonian times. So we read in Carl Boyer's book, A History of Mathematics, the solution of a three-term quadratic equation had been handled effectively by the Babylonians in some of the oldest problem texts. For instance, one problem calls for the side of a square if the area less the side is 14,30. The solution of this problem, equivalent to solving x squared minus x equals 870, is expressed as follows. Take half of 1, which is 0,30, and multiply 0,30 by 0,30, which is 0,15. Add this to 1430 to get 143015, and this is the square of 2930. Now add 0,30 to 2930, and the result is 30, the side of the square. The Babylonian solution is of course exactly equivalent to the formula x equals the square root of p over 2 squared plus q plus p over 2 for the root of the equation x squared minus px equals q. Note that the numbers quoted in this passage are expressed in base 60 or sexagesimal, which is the base that the Babylonians apparently tended to use to express numbers rather than base 10, in which numbers are more often than not expressed in modern mathematics, but I won't go into any more detail here with this. Diophantus of Alexandria was a mathematician living sometime in the first few centuries AD, though it isn't known exactly when. Diophantus is best known to us through his famous work, the Arithmetica, which shows how a variety of equations, including quadratic equations, can be solved. Due to the limitations of symbolism and limitations in the understanding of the concept of number, mathematicians in the past have often viewed things, and in particular quadratic equations, very differently to how they might be viewed in contemporary mathematics. For example, negative numbers were still not properly accepted as numbers by mathematicians until the 19th century. The ancient and Alexandrian Greeks had no concept of negative number. Irrational numbers have been another type of number that, although fully accepted by modern mathematics, took a long time to be fully recognised as numbers. In Thomas Heath's translation of Diophantus' Arithmetica, we see that since Diophantus didn't acknowledge negative numbers, he was forced to express quadratic equations in several different forms, which modern mathematics would be able to treat as the same form. The different cases that Diophantus distinguishes are, according to Heath, Case 1, mx squared plus px equals q. Case 2, mx squared equals px plus q. And case 3, mx squared plus q equals px. In Jean-Pierre Escoffier's book, Galois Theory, we read, Al-Khwarizmi appears to have been the first, around the year 830, to have pointed out the existence of quadratic equations having two strictly positive roots. Negative roots were taken into consideration only around the end of the 16th century. And again in Boyer we read, until modern times there was no thought of solving a quadratic equation of the form x squared plus px plus q equals 0, where p and q are positive, for the equation has no positive root. Consequently, quadratic equations in ancient and medieval times and even in the early modern period were classified under three types. 1. X squared plus px equals q. 2. X squared equals px plus q. 3. X squared plus q equals px. All three types are found in Old Babylonian texts of some 4,000 years ago. The division of quadratic equations into different types that Boyer gives matches up with the division that Heath gives for Diophantus. So what I've presented here on the history of quadratic equations is only scratching the surface. There's so much more to the story than what I've chosen to include in this video. So I encourage you to look further into the history of quadratic equations and mathematics in general, and it's surprising what you can find out. So that brings us to the end of this video. Thank you for watching this video right to the very end. If you made it this far, then I hope that you found the video interesting and that you found it useful. Please subscribe to this channel and hit the like button to show your support. I'll be uploading further videos to this channel over the coming weeks and months, and if you have any suggestions for any topics to cover, then please let me know. So goodbye, and I'll look forward to seeing you in the next video.